Here we are again in our adventure of gas laws. And if you remember with our gas laws already, we've seen Boyle's law if you're watching these in order. If not, a few things to remember about these gas laws. Mass stays constant. Okay. In this particular instance where we're dealing with Charles' law, the other piece that stays constant is we're at constant pressure as well. Right? We want to make sure that our pressure is constant. And what Charles' law is it's this relationship between volume and temperature when you're dealing with a gas. And if we take a look at this graph, as the volume increases, so does the temperature. So this tells us something about how those two things are related. We know that the volume is going to be proportional to the temperature. If the volume goes up, the temperature goes up. If the temperature of a gas goes up, the volume of the gas is going to go up. Assuming though that you're keeping a constant pressure and that mass is constant. So again, with this proportionality, we can convert it into an equation like we saw before. So to convert it into an equation, we just multiply it by a constant and we'll call it K. Again, K does not matter for this. We never calculate K. We don't do anything with the K. It's just the key as to how you get it into this proportionality. What becomes really important for us though is what we do with it. When we get K by itself, we're going to get V divided by T. And this is at a set of conditions. Let's call it condition 1. Okay. If we were to change that gas from being at this set of conditions to a different set of conditions, let's call it V2 and T2, the K value still has to be the same, right? So we use this when we're comparing a gas at two conditions. So again, if we're comparing them, we know at the one condition our constant has to be the same as the constant at the other condition because it's the same gas, they're just different conditions. And that allows us then to say that V1 over T1 equals V2 over T2. And this is what becomes really important for us when we're dealing with Charles' law and we're looking at how a gas behaves. When we look at that relationship between volume and temperature, we know a gas at one set of volume and temperature conditions should be equivalent to that ratio of volume and temperature in a new set of conditions. And this is what we use when we're dealing with Charles' law. So let's try an example. Miss Hammond got a balloon filled with 2 liters of helium gas in a store where the temperature was 21.5 degrees Celsius. The balloon was placed in the car as she continued to shop. The inside of the car was minus 7.5 degrees Celsius. It was winter. When she returned from shopping, the balloon had shrunk. What was the new volume of gas inside the balloon? Okay, so again, like any other question, keep track of what we have. We know that initially the volume was 2.0 liters. We know that the initial temperature was 21.5 degrees Celsius. We know the new temperature is negative 7.5 degrees Celsius. And we want to find the new volume, right? That's the key. Now, one thing with gases, we can't use units of degrees Celsius. We have to convert this into Kelvin, right? Both temperatures have to be in Kelvin to be used when we're dealing with gases in these calculations. So again, to go from Celsius to Kelvin, we just add 273. So 21.5 plus 273 would be 294.5, and the unit now is Kelvin. Minus 7.5 degrees Celsius, add 273 would be 265.5 Kelvin. Okay, so now that we've got our temperature in the unit Kelvin, now we can do our calculation. So we set up our ratio V1 T1 equals V2 times T2. And then we just rearrange to get V2. So V2 is V1 T2 over T1. And plug in your numbers. So volume initially 2.0 liters. Temperature 265.5 Kelvin for my temperature 2. My temperature 1 was 294.5 Kelvin. And then we do the math. Punch it into your calculator, and you should get 1.80305, which to the right number of sniffing digits, the smallest number is 2 in this calculation, and it's all multiplying and dividing. So I should end up with 2 sniffing digits. It now is 1.8 liters. Okay. And again, if we were keeping track of these units, notice that my Kelvin units cancel out, right? So the Kelvin units are gone. I'm just left with liters. That's how I know my volume has to be a unit of liters, right? So Miss Hammond's balloon shrunk to a new volume of 1.8 liters.